Загружу сам, что ли?
Ну давай.
А рекординг пошел, да? Там.
Ну, должно. Да, должно. Ну, смотри.
Да, ну посмотрим, что будет.
Нет, мы не транслируемся. Okay, dear colleagues, let's start our seminar. Today our guest is Professor Bordag from JINR. He will tell us about tachyon condensation in the chromomagnetic background field and the ground state of QCD. So please.
Спасибо за приглашение. Разрешите все-таки прохладно. Хорошо, доклад буду делать на английском. Если есть вопросы, то сходу задавайте. My topic today is tachyon condensation in the chromomagnetic background field and the ground state of QCD. I think everybody had already opportunity to read the abstract. The talk is on the following topics: the chromomagnetic vacuum and the problem with its stability, and then a field theory with the tachyonic mode, and symmetry breaking by a condensate of tachyons, symmetry restoration in the Hartree approximation, and some conclusions. Let me start with the chromomagnetic vacuum and the problem with its stability. We consider QCD in the usual fashion. This is the SON, non-abelian field strength, and we consider a chromomagnetic abelian background field. That means this is this weak shift of the quantum field, which is a magnetic field in the third direction in the group space, and in a gauge in the so-called symmetric gauge, which gives this is a potential of the background field, which gives a constant magnetic field overall in the space of strength B. And then in quantum dynamics, the effective potential follows as a generalization of the Heisenberg-Euler-Lagrangian in QCD, and it reads the effective potential is the classical part, d squared half, and then there comes the one logarithm from the one loop contribution, and here in front is the first coefficient of the beta function with the corresponding sign. And then there is an imaginary part, which we will discuss on the next slide. Because for small b, this log is negative, the real part has a minimum below 0 at finite b. The value of b in the minimum is given by this formula, and the effective potential in the minimum is given by this formula. If you do the same in electrodynamics, in the real Heisenberg-Euler-Lagrangian, then we have here a minus sign, and there will be no minimum. So this existence of this minimum is a effect which is equivalent to the asymptotic freedom. Because this minimum is below 0, the corresponding magnetic field is one spontaneously created, and it provides the new ground state of quantum chromodynamics. And this ground state is a so-called Savvidy vacuum.
And G is the renormalized. G is the band from me.
No, without any renormalization. That is, so to say, symbolically, it's a coupling of QCD.
Sorry?
It is symbolically the Kaplan constant of QCD.
And what is mu there? Scale mu.
Yeah, mu is the usual the usual scale factor which comes in by from the regularization.
From the regularization of
Yeah.
what?
Of the one loop graph.
One loop.
Yeah, say in dimensional regularization. Yeah, you have to introduce an
Okay.
arbitrary mass parameter, and that is mu.
And you don't want to introduce this mass parameter to regularize G, coupling constant.
This parameter it comes in with a regularization, but itself does not regularize anything. You simply
This is one loop.
you write some
One of
momentum
G
k
is G.
squared to the power of s, that is a regularization.
Huh?
And to keep dimensions, you have to introduce an arbitrary regularization parameter, an arbitrary mass parameter. Yeah? And after the normalization, it remains. Now you take the pole part, and after that this dependence remains. If you go to real physical theories, then usually at this place lambda QCD appears. But I'm not going to do this, at least at the moment. So that is, so to say, the idea which was spelled out by Savvidy in 1977. However, the spectrum of a charged particle in a magnetic background field is a has this well-known structure where n are the Landau levels and s is the spin projection, which for the gluon goes with a factor of 2, yeah? And then you have one state for n equal to 0 and s equal to -1, which goes with a minus sign here. Yeah? In electrodynamics, you have in place of this factor of 2 a factor of 1, and the lowest state is 0, and then you have in addition in this formula the electron mass. So that in electrodynamics there is no such instability, it's a pure chromomagnetic effect. And further, since this one particle is a one particle energy, yeah, it's below 0, you have as a consequence an imaginary part in the effective action, which can be viewed also as a negative mass squared. And for this reason, this mode is frequently called a tachyonic state and also unstable state. And this imaginary part, makes this vacuum, Savvidy vacuum, of course, unstable. Yeah? And here two comments are in order. If you take the contribution from the stable states, that are all states except of this one, you get also a negative effective potential, and you have simply to replace this element, which comes from the beta function, by 6. No.
Excuse me, Mikhail.
By 5.
Maybe I misunderstood something. You are claiming that G is not dependent from gluon is not dependent from mu.
And a pure one loop.
At one loop.
Yeah.
It is only one loop.
Only one loop.
Only one loop. But then it will depend from mu, but in the one loop level. Okay?
It will depend on
the one loop level.
Yeah.
Okay. So we are considering one loop approximation.
But you see,
The normalization group improvements, yeah, it is a different story.
I don't understand. My point is that in the minimum region, when you have this effect, you have a strong coupling regime. You can't trust one loop approximation.
Again, in the minimum, yeah,
You see, the minimum takes place, non-trivial minimum, takes place in the infrared region. In the infrared region, effective coupling constant is not small. Therefore, you can trust this one loop approximation.
that's true. When the coupling is small, this minimum is extremely shallow, yeah, and so that is another objection against this Savvidy vacuum, yeah, that this effective, this minimum is by far too shallow to be physical. Yeah. The next objection is that it's not stable. Yeah. So what we are speaking about, because of the imaginary part, is not stable. Yeah, and there's a further objection. A further objection. The spontaneous generation of the magnetic field in the chromomagnetic background is a symmetry breaking, of course. Yeah.
Which symmetry?
The homogeneity of space, at least. Yeah. And it was shown about 20 years ago that this symmetry, that the symmetry is not restored at high temperature. People simply they considered this whole thing at high temperature, and they found that there also a minimum, a non-trivial minimum is present. That means that the symmetry is not restored at high temperature. That is another objection what concerns this Savvidy vacuum. Then there, over the decades, there have been a number of attempts to remove the instability. The most famous one is the so-called Copenhagen vacuum. Here is the basic citation, or which is then also what called the spaghetti vacuum. I'm not going to comment that further. It had been abandoned. In another paper, in two, also quite soon after, quite early, the idea was spelled out that the self-interaction of the tachyonic mode, so far what we consider in one loop, is only the quadratic part of the action. Yeah, because of however it's non-abelian, it is also a quartic part. And if one, this self-interaction takes in, if one takes it into account, this should remove the imaginary part, like this happens for a quartic oscillator in quantum mechanics. In another paper, together with Vladimir Skalosubin from Dnipropetrovsk, we made an attempt to sum the so-called ring diagrams or Daisy diagrams using the polarization tensor in some fractal approximation to try to get rid of the imaginary part. For these two things, the common outcome was, the common conclusion was that one may disregard the imaginary part, while keeping the real part without changes. However, quite recently, we undertook an attempt to calculate the minimum of the effective potential when, in addition to the chromomagnetic background, also a constant A0 field or a Polyakov loop is present. This was motivated by a lattice calculation in Nepomukhov's, where a minimum in the A0 B plane was seen. With no, of course, it is by lattice, by construction, so to say, with no imaginary part. However, the two-loop calculation which we made, and two-loop one needs because the minimum as a function of A0 appears only in two loops. In one loop, it's not present. A very unnatural behavior of the real part of the effective potential in the A0 B plane was found. It's simply that in the middle of the plane there's a breakdown to minus infinity, which of course should not be there. And this behavior puts into question the above mentioned conclusions from two different sources that the real part stays in place when one does sufficiently many, the one or the other thing, to remove the imaginary part.
Human, is there any gauge dependence?
This question is still open, not investigated.
But at the tube level, it should be, I guess.
Possibly, sure. But we did not look on the gauge dependence. First, we have been interested in what happens, so to say, in a given gauge.
And what kind of gauge do you use?
Covariant gauge. But there should not be much dependence on the gauge concerning the basic facts, whether the real part after these manipulations is okay or not. Yeah? So the conclusion was that two loops are clearly insufficient to get a reasonable result. What I now suggest is a new solution to the problem with the imaginary part, and consists in the application of the Higgs mechanism to the unstable mode. The unstable mode is defined by the quantum numbers all P0, all P3, n equal to 0, and the spin projection -1. This way, it represents a complex scalar field depending on the remaining two variables in the momentum or in coordinate space, with a negative mass square and a quartic self-interaction. And this field is living in the remaining two dimensions, and then the corresponding Lagrangian reads the quartic part of this kind and the quadratic part and the quartic self-interaction part of this kind.
Sorry, psi is what?
Psi is a scalar field, is what remains from the tachyonic mode. And in a moment, no, I will not show it. In a moment, you have the tachyonic mode. It depends on all n, all s beyond these momenta. And then you take only special values. All other you forget. What remains is a field which depends on two variables.
Basically, you parameterize your A mu as some known function of angular variables and psi.
The gluon field has a Lorentz index, and the dependence on all variables. Yeah? And then I write 1, I, 0, 0, that is a corresponding Lorentz structure. Then I write down U0 of x perpendicular. That is also the later function corresponding to the lowest lambda level. And what remains is the letter psi. Yeah? And in the corresponding represented complex field. Yeah, after turning the basis. And so this is what remains if I take only the tachyonic mode. It's a two-dimensional theory with a quite simple Lagrangian. The mass with a wrong. sign is given by the magnetic field. Yeah, that is the interaction of the magnetic moment with the background field. And one can show that the corresponding Kaplan constant depends also on the magnetic field. You have to integrate over force power of these oscillator functions. The second power integral over second powers is a normalization, gives 1, of the force power gives b times the number. Yeah? And this comes here as Kaplan constant. It must be dimensional, yeah, because it's a two-dimensional theory. So, and now I have a quantum field theory for the tachyonic mode in 2 dimensions with a quite simple structure. The remaining part is a matter of techniques. So let me repeat, consider SO2 dropping all modes except for the tachyonic one. And of course this should be understood as a first approximation in the assumption that the tachyonic mode captures the essential basics and that the remaining modes can be handled as some preparation later on. Here is the background, and then the initial formulas are this one, and then we turn the potential to this W to get charged fields. And then we have the interpretation that the A, the third component, is a neutral scalar vector field. And here we have, from the other components in color space, we have a charged vector field. And we have the, for this the corresponding covariant derivative, which depends on the background field. Yeah, and here I repeat the structure, which is the quadratic part of the neutral field, that's the quadratic part of the charge vector field, and that is a quartic part of the interaction. And then this is a formula for the tachyonic mode, two-dimensional integration into 3 and 4th directions, because already in a Euclidean formulation. That is a Lorentz structure. That is an oscillator function e2 minus b to the 4th x squared is a normalization factor, and that is a remaining field in momentum representation here. So these are the specific formulas, and then we introduce the Fourier transformation back, and drop all other modes, and then the remaining action takes this specific form. And here we use what I already mentioned, that this integration of 4th order gives just a factor b times a number. Yeah, so what further if we have a theory with a negative mass square? We have essentially, since it's a complex field, we have essentially this is equivalent to an O2 model with 2 real fields, and we can write this as a Lagrangian or an action with 2 real fields, and again these notations. And then what is an essential step, like in the Higgs model, one must make a shift of one of these components. Usually these components are called usually Higgs and Goldstone fields. Usually one makes a shift in the Higgs field, what, however that is arbitrary, and this realizes the symmetry breaking, and then the field after the shift is a remaining quantum field. And also this letter small v is a condensate. With this shift, one introduces new masses, yeah, which acquire contributions from the shift, and then in the further course of calculations, we follow this paper where we considered the temperature phase transformation, transition and an effective expansion parameter in the ON model in 4 dimensions, but the formalism, the basic formulas remains the same, also in 2 dimensions. What happens is that in that approach, the propagator is considered as an arbitrary argument, and one takes the Legendre transform with respect to this argument, to this propagator. It's in fact not a second Legendre transform, but this is what it's common saying, with respect to the second correlation function. From here, the second comes here. The result is a representation of the free energy in terms of some explicit contributions, and all remaining contributions are expressed in terms of 2-particle irreducible graphs with a new propagator function beta and also with the usual graphical structure. The first part is a tree contribution, or the classical part. Then for both fields, eta and phi, we have the trace log contributions, and then some factors which follow from the combinatorics, where delta is a bar propagator, so also free propagator, and beta is a new, is a full propagator. The above representation is equivalent to a resummation of all daisy diagrams or mass insertions, sometimes also called foam diagrams. The price for this resummation one has to pay is now that these propagators beta are arguments to the Schwinger-Dyson equations, or one has to solve these equations to get the propagator. Sigma is a second derivative, is a derivative of the 2-particle irreducible graphs with respect to the propagator, a functional derivative, of course. In this way, one has a reformulation of the theory with an infinite resummation. This is a thing which is known, by the way, in statistical physics under different notations. It was known already in the beginning of the 60s of the last century. And in quantum field theory, it has first been applied in temperature field theory in the beginning of the 80s, if I remember right, in a paper by Cornwell, Jackiff, Tombolis. It's also called CGT formalism.
Why do you need it here? What's the point to use this formalism here?
To handle the negative mass square together with a shift, and to get finally to come to a high temperature. To be able to do all this at temperature.
Oh, okay.
And in order, and the point is, these resummations of all these graphs is necessary to get rid of the imaginary part. If you go back to the formula for the mass, you do not know what is the condensate. And if the condensate is too small, the new masses are still negative.
Yeah, but you have sort of Higgs theory, right?
Sorry?
You have Higgs-like theory. Why don't you simply do the
conventional? The point is, look, if you do not do this resummation, then say 2, 3 loop graphs, all this, they get mass insertions which reproduce the infrared, the bad infrared behavior. Yeah? And only after
Oh, right, you are in 2 dimensions, right, okay.
Okay. Now, in 4 dimensions it's the same.
No, it's...
For instance,
No,
if you sum only the simple daisy graphs, you get not rid of the imaginary part.
Yeah, but you shift your field, so the masses, effective masses are positive.
Yeah, but after that you have to look for a minimum of the effective action with respect to the shift.
Yes.
And in this minimum, the imaginary part must vanish.
Right.
Yeah, and the value of V is defined by the position of the minimum.
Right.
If you do only simple daisy resummations, at least in 4-dimensional theory, people have seen that the imaginary part does not go away. That was a series of papers in the beginning of the 90s.
Okay.
Yeah? And only if you where did it go here? Also the so-called super daisy, that when you have a insertion and into that another insertion, and all these possibilities, only after summation of that, you get rid of the imaginary part in the minimum. So, that is a general theory, which is of course pointless unless you don't know all graphs. One has to make an approximation. And the lowest approximation is the so-called Hartree approximation, not Hartree-Fox. It would include the sunset graph. And the lowest graph, the first graph, which is 2 particle irreducible, is the 8. Yeah? And since you have 2 fields, you have 3 graphs of this. The solid line is the Higgs field, and the dashed line is a constant field. But these are simple graphs, and you have explicit from them analytic expressions, where these sigma with a upper index naught are simply simple loops. That is simply the trace of one propagator, and these are constants. They do not depend on the momentum. This independence on the momentum, which happens only in this Hartree approximation, gives us the possibility to make the ansatz that the propagator, the new propagator, is only the old one with a new mass. The same structure as the old one, but a new mass parameter. And then the Schwinger-Dyson equations turn into gap equations, where you have only to calculate the new mass. These functions which appear here have a 0 temperature part, which is simply the log from the one loop. It's a one loop log. And then a temperature-dependent part, which can be expressed either as a sum over Bessel functions, or there's also an integral representation.
Excuse me, why mu is 1 in the following?
For simplicity. I'm not to get physical answers. I'm going to show the possibility to get a consistent theory, not more.
Excuse me, what? You want to show, I missed the last one.
I'm going to show that one can get this way a stable theory with no imaginary part, and another property I'll discuss a little bit later on.
And that is why you are simply considering the normalization point mu is equal to 1.
Yeah, yeah. It is, for this conclusion, it's unimportant. You can take 10 or whatever you like, not 0, of course. These are simple formulas for the one loop graph and similar formulas for the
But is it related to the one loop your one loop considerations? If you will consider, say, two loop analysis,
much more complicated. Yeah. The point is, in fact, these are infinitely many loops, but in this approximation, in this scheme, it reduces to insert this one loop contribution into the gap equation. Yeah? So from all, this is some subclass of the or simple part of these all loops. Yeah? Which is governed by the combinatorics given by these equations. Yeah? This makes the thing so easy from the technical point of view. If you add, for instance, here the sunset graph, which would be the next, things would become much more complicated. For instance, you would have in this equation the momentum dependence, and not trivial one, and so on. So, and then we have the effective potential in Hartley approximation. If we insert what we have the solutions of the gap equations. This give us the capital M eta and M phi. Then these known expressions, quite simple expressions for the simple loops, and similar for the trace log. And that is it. And then we can investigate this expression, at least numerically. So using the solutions of the gap equations, this effective potential becomes a function of the condensate, and the parameters, the initial mass, lambda and t, mass and Kaplan lambda, have been expressed through the background magnetic field, if we return to what we need this for. And these gap equations have always, for all values of v and the other parameters, a real solution. And it's to be mentioned that this is a result of the resonations, and this happens already at 0 temperature. And this is a little bit in difference to the four-dimensional case, where it's where real solutions appear not. This is up to the origin, not very close to the origin. In 4 dimensions you have imaginary values, which nevertheless allow for real values in the minimum. So this is more convenient. And with the above formulas in our O2 model, after symmetric breaking, a phase transition may be investigated numerically at finite, and the result is a first order phase transition, where you get the usual picture. For this effective potential as a function of the condensate, you get these curves for low temperature. For instance, for 0 temperature, you have a quite deep minimum, and for higher, raising the temperature, it becomes, it raises up until it becomes higher than the perturbative minimum at the origin. And that is the point of where you have the critical temperature, when the system goes from this minimum to the perturbative one, and the symmetry restores. That is a picture typical picture of a one first order phase transition. And there is a comment in order. For general reasons, one would expect a second order phase transition where this maximum not appears. But this is a known defect of the Hartree approximation. Everybody or most people are convinced that if one includes higher order graphs in this approximation beyond the Hartree, that then it should disappear. However, the basic pictures, the symmetry breaking at low temperature and its restoration at high temperature are correct, or even in the given lowest approximation. These are only the details near the phase transition which do not come out correctly in this approximation. Those are
Again,
basic.
what is the symmetry you're talking about? This is
The symmetry is sitting here, it's origins, it's a perturbative vacuum.
This
No
O2.
no
Is
condensate,
this
no
O2
background
symmetry?
field.
No, which is the O2 symmetry of your two-dimensional theory or what?
Look, if you have this gluon field. And one mode, you give an addendum plus V,
Yes.
you break more or less any symmetry of the system.
Mhm.
Yeah? And the background field breaks homogeneity of space.
Mhm.
I cannot tell you exactly which symmetries are broken, which remain. I'm not able to say this.
Mhm.
But that's our broken, it's obvious.
Okay.
Yeah? Okay. Let me remind you that the parameters B and the Kepling, here it should be lambda. This is an example for specific values of the parameters. It depends on the magnetic field, on the background field. So the whole picture depends on the background field. And for to consider the complete effective potential, one has also to add the classical energy of the background field, of the magnetic background, to the effective potential. And in fact, we have to look for a minimum of just this expression. And this is what comes in place of the initial Heisenberg-Euler formula I showed on the first sheet. Now, a numerical evaluation shows a minimum in the plane of the two parameters, V and B. That is a condensate and that is a background field. At zero temperature, in the left panel, the minimum is somewhere here. The zero level is on this color. It's somewhere here, so all this is below zero. And then raising the temperature a little bit, this minimum becomes higher. Now in this color, the zero level is here. And this corresponds just to in the previous picture, what we have seen was a section at a given value of B. A section, a horizontal section of these pictures, and now, and this is not the origin, this is taken, the interval here is taken to get a nice picture, of course. And if we raise the temperature further, then everything deforms, but this minimum is here, but another minimum at the origin appears. And if further raising the temperature, this one becomes the deeper one. In fact, it here it's something here. This is 0, but this is not 0.4. No, it's something here. It's origin, yeah. But again, the scale is taken in a way to show both minima in one picture. So, and here I plotted the minimum here as function of the temperature, and it's seen that it goes up, and this is a picture more or less at the phase transition, and it corresponds to this point. If we go higher, then this is a deeper minimum, the system goes here, and the condensate and the background field disappear, and the symmetry is restored. This way, and of course in the whole thing there is no imaginary part, and in this way I have a new model for the vacuum of QCD. It rests on the assumption that the unstable mode in the chromomagnetic background forms a condensate, and this means that the tachyonic mode is quantized around this condensate, and that the corresponding effective potential is lower as a perturbative one. In this way, the original symmetry will be broken by magnetic background and condensate. This situation is similar to the Higgs model and the Mexican head potential. And did I mention? And to realize the above proposition, I assume that the basic features can be investigated when all other modes are neglected, except for the gluonic one. And so we have in the result an O2 model in 2 dimensions with the mass and the coupling, which depend on the background field. And then we have seen raising the temperature, the mentioned minimum becomes shallower, second minimum at the origin appears, which becomes the deeper one, and this way symmetry will be restored. That is the result I have. And I hope that the observed tachyon condensate will open a new window for the confinement problem. Now we know in the confinement in this from lattice that there's a lot of condensates, but all these are somehow introduced by hand. And here is a way where the condensate comes in, so to say, in a systematic way. And over the past decades, a much discussed question was, what happens to the unstable tachyonic mode? And what I give is a physical answer that from this instability, tachyons are created, such modes, field modes are created, that much until these come into equilibrium with their repulsive self-interaction, and that they form in this way a stable condensate, which is something relativistic Bose-Einstein condensate. Usually this notion BEC is reserved for non-relativistic theories. Now, these are my conclusions, and I use the simplest model, and further steps should be account for instance, for the back reaction of the condensate to the background. It gets here an addition, and this condensate will modify the initial background. Then the question is, this is a homogeneous background. Which background else allows for tachyonic modes? I don't know. I've never seen in literature. And so the question is to consider non-homogeneous background. For example, what is the next example would be a center of group vortex. This is a cylindrical magnetic field. Next problem would be to account for stable modes. For instance, if one adds only the neutral field, then a kind of modified abelian Higgs model appears, where the Higgs is in 2 dimensions, with a specific coupling to the abelian vector. And many other questions.
Thank you very much. Let's speaker.
The magnetic condensate breaks Lorentz, right?
It breaks Lorentz.
Yes, but we don't see any Lorentz violation in our world, in QCD, right? How are you going to restore Lorentz invariance in this picture?
I have no idea at the moment. I'm sorry.
So your picture is that indeed in QCD like theory you would expect.
There have been many speculations, you know, for instance, in the Copenhagen group, with domain walls and so on,
That's
which resulted in the spaghetti
No,
picture.
you are kind of orthogonal to this picture.
Hmm?
You are orthogonal to this picture because you have homogeneous condensates everywhere. It's not. No,
Maybe a
spaghetti
string like condensate will have a lower energy. Who knows?
And still, can one loop approximation be trusted?
Sorry?
Can one loop approximation be trusted here?
Can one loop approximation
Yes.
Yes.
Can one loop approximation be trusted here?
trusted? Trusted.
It's
Yeah.
information of foil crafting.
Yes, yes, this is.
You look, but what I'm saying now is a pure speculation. What is the main problem for perturbation theory in QCD? It's a zero, it's the absence of mass in the gluon propagator. I have a mass from the condensate. I don't know, but
in this picture, you don't include the one loop in your calculations. You don't include the one loop contribution to the, original Savvidy contribution to the.
it's included. It's an infinite summation. There's the lowest, absolute lowest
But your
term
calculation,
is Savvidy.
in your calculation, you forget about massive modes, right?
About
Massive modes.
massive.
Yeah, which means that you only keep the magnetic field and one tachyonic mode, right?
Yeah.
And this means that you don't have, all the other modes that contributes to
Yeah.
logarithm, right?
Yeah. That is this point.
No, but when you go,
Moment.
yeah, right,
Here. It's this point.
right. So basically, you begin with sort of Heisenberg-Euler Lagrangian, right, which has logarithm, right, and then you forget about this logarithm. Is that correct?
And then you forget?
About this logarithm.
No. If you do.
Yeah, you added
Wait
this
a
square
second.
term, right?
Wait a second.
You didn't add anything but.
Wait a second. If you look on these formulas, if you expand formally, you get everything back. And for instance, this logarithm, when you substitute this eta, this so to say changed mass by the Baumann, then you get back that logarithm which it was considered by Savvidy, more exactly with zero mass.
I don't understand. You
No,
say
no,
that
again.
you say that you forget about higher modes, right? Just
No, there are many higher modes.
just tachyonic mode.
First, I forget all modes, for instance, is n equals 1, 2,
Right.
and so on. And with the also spin projection.
Yes.
Then,
And then you're back.
then I
you're into
make
dimension.
the approximations that I have only from all two particle irreducible graphs only one left.
Yeah,
All
but
higher
but
graphs.
this is two-dimensional theory, right?
Huh?
Do I understand correctly? This is two-dimensional theory.
Yeah.
So you don't have higher modes. You don't have this.
No, all the higher graphs are present still in principle.
No, in principle, but in your real calculations, you don't have log. You have log v square over v square.
I'm restricted to this approximation with one graph only.
Right, which means that you don't have this v squared logarithm v squared, right? In the effective potential.
Look here, that is if you consider here, you see the Dyson series.
Yeah, but this is two-dimensional Dyson series.
No, the Dyson is a geometric series.
No, but it's
Independent
two-dimensional
dimension.
theory.
The entries are result of a two-dimensional.
So you're in two dimensions, basically,
Yeah.
right?
Yeah. But the geometric series as such
No, I
remains the
understand.
same.
I understand, but you're in basically in two dimensions,
Yeah.
right? Okay, so
And this is to the first power minus first power. This is in the denominator. If you re-expand this, yeah, you get a series, powers of logarithm, just of this logarithm. Yeah? You get powers of the one loop logarithm. Or in other words, all these one loop logarithms are summed up.
I'm not quite sure I understand what's going on. Because at some point you say you forget about higher modes, right?
It's a different thing, a different approximation, which is also made here. You can do in principle all this business with a resolution and Schwinger-Dietrich with all modes, or
Yeah,
with five modes.
But you only keep one mode, right?
And do something.
One mode,
One mode.
it's an infinitum of modes. It depends on two variables.
Yeah, of course. One mode.
In this
One
sense,
two-dimensional mode. That's what you're doing.
one two-dimensional.
One two-dimensional
Yeah.
mode, right? So the other modes will supposedly give you logarithm, b squared logarithm b.
They will also give logarithms, yes,
They are not included here.
not included. Well, the aim is that the basic point. The basic point is to get a mass.
Yeah, I understand.
Yeah. And all other, once you have this, and you have, so to say, a starting point for the perturbation theory for all other things, which is finite, and which cannot accumulate more, infrared singularities. Yeah? Then all other should be small corrections.
So your logarithm here, down here, is a two-dimensional logarithm, right?
Now, so,
Is a
it
logarithm
resides from a two-dimensional graph.
from two-dimensional theory.
Yeah.
That's
Simply
d to k over k squared.
d to k divided by k squared.
Plus m squared. So basically, your original motivation has nothing to do with your real calculation.
Again?
Your original motivation that you have instability in magnetic field is not relevant because you are doing completely different calculation.
No.
This logarithm is not the same logarithm as Savvidy. It's a different logarithm.
the logarithm from the initial calculation,
It's the full-dimensional.
it comes from here.
Yes.
Yeah? And this gives, by the way, from the 11, it's a 6. Yeah? The 5 comes from the stable modes.
Mm-hmm.
And the remaining part comes from this one.
And
That's
this
the
is this order.
Yeah.
Fine. Okay.
Yeah. So if I calculate with this,
Mm-hmm.
the beta function,
Yeah, you get 6 instead of 11.
Any more questions?
May I do some comment? Do you know Alexei from Joint Institute of Nuclear Geology? We performed some calculations on the lattice in SU3 dynamics, and we did not fight this tachyonic mode. We calculate.
you are working with the self-dual background.
What?
You are working in the self-dual background, where the background field is self-dual, right?
Gauge, real gauge fields, gluonic fields, we consider.
Yeah,
Yes,
and you
and magnetic.
consider you have a background field.
Yes, yes.
This background field is not only magnetic one, it has also electric component, right?
No, we did not consider electric component. We consider only we consider gluonic fields and magnetic fields in symmetric gauge, usual magnetic fields on the lattice, and did not find this mode. We calculated.
You should show me.
lattice.
You should show me.
No, yes, it's interesting. Yeah, I think maybe this is connected that you consider O2 model.
No.
It's,
You should show me after.
yes.
Yeah.
Any more questions or comments? If no,
May I ask?
yes, sure.
Maybe I didn't quite understand. Why do you consider a non-relativistic Landau spectrum only and not a relativistic?
Oh. Let me show you. It is
No, it's a relativist.
here. The spectrum is relativistic. And the non-relativistic, you would have here a first order of the energy. And here it's a second order of the energy. Did I answer your question?
Oh, yes. In relativistic case, this spectrum, okay, Landau.
The right-hand side is the same. The difference is only here in the power of the energy.
Okay,
Okay?
are you satisfied?
Thank you.
More questions? Well, if there are no more questions, let's thank the speaker again. Thank you.
Ага, я поняла, да. Вы вот это, если это
А вы с Олегом? Ага.
ну да, ну мы работаем.
Да. Вы тут не бываете?
Ну да, как когда надо. Ну я там сейчас мне там надо пропуск получить, чтобы сейчас да. В общем, я когда приезжала, мы с ним обсуждали, я сейчас просто, ну, как-то заинтересована, была это. Мне просто другие вещи.
Но я до конца думаю, что он не до конца
я ему напишу, и просто
У тебя были завязаны,
да я напишу сегодня вечером.
Спасибо.
Это вам
Потому что есть